Hi learner, I welcome you on board to this session. The topic of this session is atmosphere and its properties, and we are also going to discuss about the standard atmosphere model. This topic is entitled to the subject flight mechanics. The target audience for this session are GATE aerospace aspirants, aerospace and aeronautical engineering students. Let's get into the session. So, getting a basic outline of this session, we are going to discuss or see about these following topics. We'll be seeing in detail about the three major properties of the atmosphere and the variation of those properties with altitude. In addition to it, we'll be seeing the standard atmosphere model and we will be deriving the basic derivations for isothermal region and gradient region of the standard atmosphere model. We will be referring the standard atmosphere chart for getting a better understanding of the topic. In the previous video or lesson, we did see about the general perspective of atmosphere and altitude. Let's get started. Atmosphere. We did learn about what is atmosphere and the major components of it and the basic perspective of it. Here we are going to know about the basic properties of atmosphere in order to develop a standard atmosphere model through derivation. Talking about derivatives, and we uh, have to know the three basic properties of atmosphere: pressure, density and temperature. Though there are several other properties, these three are the major defining factor of a standard atmosphere model. And the main function of these three properties are they vary with altitude, that is they are varying as a function of altitude. Here, a standard atmosphere chart, that is International Standard Atmosphere Chart, developed by US Air Force, is provided. Here we can see that the pressure, density, temperature, and speed of sound is varying with altitude. So altitude is taken as reference, and the variation of these properties with altitude is traced over here. We can see from the plot that pressure and density terms are decreasing with increase in altitude, and the temperature is relatively varying with increase in altitude. Speed of sound is not referred for now. So, what is the need for a standard atmosphere model? Standard atmosphere model is a static model in which mean values of pressure, density, and temperature change along the altitude range is known as standard atmosphere, as it is provided over here. What is the need for it? As we know, atmosphere isn't static; it is dynamic. So, for the purpose of engineering calculations and for the purpose of pilot, we need to know a standard reference for calculating the properties at that situation or a particular altitude. So for it, we need a static value, that is an averaged or mean value of the properties. So this static model of atmosphere provides a standard uh, values for calculating the pressure, density, and temperature if we know the altitude. So, talking about the atmosphere, we have two kinds of regions, that is, the region where the temperature is constant and the region where the temperature is varying. So, the region where the temperature is constant is known as the isothermal region, and the region where the temperature is varying along with temperature altitude is known as gradient region. So this is basically the gradient region, and there are approximately four gradient regions in international standard atmosphere. And the isothermal region, we have the constant temperature. Iso means constant, thermal means temperature. So as we see, these regions are known as the isothermal regions. What is lapse rate? So temperature is varying with altitude. It is either decreasing or increasing with altitude. Here the temperature is given in Kelvin terms, that is units, and we can see in decrease over here, and perpetually the temperature is increasing in some regions. Okay. So this is actually following some rate. It is evident that it's visible as a slope. So this slope has some value. This is known as lapse rate. So lapse rate is the rate at which temperature varies with altitude. And if we know the temperature at the topmost point of the slope and the bottommost point of the slope and the height of the slope, we can provide or create a rate, and it is known as lapse rate. Here we can see that different lapse rates are provided. It is A1 to A4, four different lapse rate. A1 is for here, A2 is for this region, A3 is for this region, and A4 is further for this region. A is nothing but the symbol of lapse rate. So here we see that lapse rate is the ratio of change in temperature by the change in altitude or height. So the lapse rate for first region, that is for this region, is minus 6.5 times 10 to the power minus 3 Kelvin per meter. And for the second region, the lapse rate is provided over here. Similarly, for four different regions, the lapse rates are provided over here. So we need to derive the properties of international standard atmosphere in order to typically obtain the standard atmosphere model in the numerical terms. So here we are seeing the pressure, density, and temperature are dependent on altitude. So for the case of international standard atmosphere, the temperature is obtained from the experimental data, that is using weather balloons or sounding rockets. So if the temperature is known from the experimental data, we can derive the pressure and density as a function of height. So there are two different relations for pressure and density with height. That is, for isothermal region, there is a relation for pressure change and the density change. And for the gradient region, there are two different relations for the pressure change and density change. So how to obtain these derivations? We are getting back to those basic equations, the hydrostatic equation and the equation of state, which we discussed in the previous lesson. Actually, we derived in the previous lesson. So here we are taking the hydrostatic equation of geopotential height. As we know, geopotential altitude or geopotential height is a height in which the gravity is considered to be constant, that is G naught. So if we are considering the hydrostatic equation, that is change in pressure is equal to negative sign of the density and acceleration times the constant acceleration due to gravity and the change in height. And the terms used over here are basically defined, or the name selections are provided over here. So next equation we are going to use is the equation of state. As we know, if we know the temperature and pressure, we can derive the density, and similarly vice versa. Similar to the previous method, we are dividing these both equations, that is the hydrostatic equation divided by the equation of state. We obtain similar kind of equation where the density terms are constant and are getting cancelled out. So we are getting an equation for change in pressure by the actual pressure. Here we can see that it is a function of height. Still, we need the explanation of the term change in height. And here we can see that the pressure is termed in the change in pressure terms, that is dP and not as P. So we need to integrate it in order to cancel out the differentiation term. We will be deriving for two different cases, that is for the isothermal region case and the gradient region case. Isothermal, as I said, we need to remember that it is for constant temperature, and gradient, as we know, it is for the varying case of temperature. First, we will derive for the isothermal case. So isothermal, as I said, the temperature is constant over here. So this is the actual isothermal region, which can be seen over here. This is the isothermal region. The temperature is constant, the steady line is the vertical axis. So this is zoomed out for our purpose. And if we consider the properties at the base of the isothermal layers are known, and they are termed as T1, P1, and ρ1. And if we need to find a property at some particular height in between this isothermal region, we will consider that height as h. So the height at the base of isothermal region is termed as h1. So considering this as what we know, we will derive what we want, the properties temperature, pressure, and density at a particular height h, that is the geopotential height. So as I said, is in differential terms. In order to get in normal terms, we need to integrate it. So when we integrate this equation, applying integrations on both sides and deriving for the pressure at a particular height h, so P1 to P and H1 to H, and G naught and RT, that is gas constant, and the temperature terms are constant, and we are just taking it out of the integration. When we integrate it here, from the integration formula, integration of inverse times the differential term is ln natural log n, ln of the term, that is P by P1. And similarly here, the dh term, we can while integrating, we can be writing it as h minus h1. So this is the result of integration, and as a result of integration we are obtaining the pressure at the height h, and we know the pressure at the bottom of the isothermal layer. So here is the equation for change in pressure in for isothermal region. So we have obtained the change in pressure for isothermal region. Now how to obtain the change in density for isothermal region? So basically here we know that these are the known terms. H1 temperature is constant, P1 are the known terms, so we can derive it for P if we know the value of observation H. So for deriving the change in density, we will use the equation of state formula, that is P is equal to rho RT. And here we are using the equation of state for two different cases, that is for the base of the isothermal layer and the observing heights isothermal layer, such that these are the conditions at the height h, and these are the conditions at the base of the isothermal layer. So when we divide it, that is P is equal to rho RT by P1 equal to rho 1 RT1, R is constant. Okay, so when we cancel out the common terms, R and R are common, and as we know, for the case of isothermal layer, the temperature is also constant, that is T is equal to T1 or T1 is equal to P. So you can cancel out both of them. Here we are getting the term rho by rho 1. So this is the density ratio. So basically for isothermal region, the change in pressure is equal to the change in altitude, density with the altitude. So both are having the same relation. So here we can write the same relation of change in pressure as for change in density. So thus we have derived for the isothermal region. Now we have to derive it for the gradient layer or gradient region. For the gradient region, we know the temperature isn't constant and it is varying with increase in altitude. So here we need to introduce the term lapse rate, as I discussed before. Lapse rate is nothing but the change in temperature divided by the change in height or altitude. So change in temperature, if we consider the temperature at the base of gradient region as T1, P1 and rho 1, and at a particular observation height h, the conditions or properties are termed as T, P and rho. We can write the lapse rate as change in temperature dt by the change in height dh. So we need the term dh over here in order to substitute in this equation. So dh is required. For obtaining the dh, we will rearrange the equation, that is take this dh term to the left hand side, and when we bring the lapse rate term to the right hand side, it turns to denominator. So we are getting an relation for the change in height dh. So the value for dh is obtained. So when we substitute the value of dh in equation 1, that is this equation or equation a, we will obtain a relation similar to this. So basically it is having a, and the common terms are grouped over here. So when this is the case, as I said, it is in differential form. In order to get in normal terms, we will integrate it in order to cancel out the differential terms. So when we integrate it on both sides, we are taking the g naught by ar, that is the lapse rate and gas constant term outside, and when we integrate it for the two cases, that is p1 to p and t1 to t, that is observing height h1 to the height h, where we need to find the temperature or the properties. So when we integrate it, the result is ln, that is log n, natural log of p by p1 is equal to minus g naught by ar, which is the constant term as it is. And when we integrate this term, we are obtaining the ln log n or natural log n of the t by t1 term, similar to this. So here we need to cancel out the ln terms on both sides. So we will just raise it to the power of e on the both sides. So the ln and the e terms gets cancelled out, and the remaining term, which is outside of the ln or log n, uh, gets into the power of the term. So here it gets cancelled out for this case. T by t1, the ln gets cancelled out, and the g naught by ar term in terms of negative gets into the power of t by t1. So here we have typically arrived the pressure change in pressure relation for the gradient region. So how do we find the change in density for gradient region? Similarly, using the previous methodology, that is by using the equation of state for both the regions, that is P is equal to rho RT time divided by the P1 is equal to rho 1 T1 R. So R and R are cancelled. When we cancel out it, the temperature isn't constant, so we cannot cancel out it. So we have to keep it as it is. So cancelling out the gas constant terms, it remains as this equation. So when we further get into this, we know that P by P1 can be written as rho T divided by rho 1 T1. So in order to get the density ratio, we will be transferring the other terms to the other side of the equation, that is RHS. So when we transfer it to the other side of the equation, uh, it will be getting into the denominator, and here as we see it is already in negative term, and when this is taken to the numerator, it will be also associated with a negative term, and when we take the negative term as constant, so here we get an addition of t by t1. And we also need to know what T is, that is the temperature at a particular height in the gradient region. For obtaining it, there is a relation which we can be using. That is, if we know the temperature at the base of the gradient region, and when we sum it with the lapse rate times the change in height, we will obtain the temperature at the observing altitude h. And we also need to assume that the variation in temperature is linear in the gradient region, but as for the real case it isn't linear, and it is dynamic or it is non-linear. So this is a basic assumption which we need to derive for obtaining the international standard atmosphere. So when we apply all this, we will be obtaining the density ratio for a particular observing height, similar to that of pressure ratio. So thus we have arrived the derivations for the isothermal layer, that is the pressure ratio with increase in altitude and the density ratio with increase in altitude. Similarly, we have also arrived the gradient layer the pressure ratio for gradient layer, and the density ratio for gradient layer. And these equations are very important from the gate perspective, as they are forming the base of many questions, or sometimes they have been asked as direct questions. This they ask the formula for pressure change in isothermal region or gradient region. So, okay, the derivation part is okay, but still it is in alphabetical terms, and we need numbers in order to pursue with our calculation. So, if we have a temperature at some altitude, so how do we derive the values of pressure and density at that particular altitude? So we know the altitude at which we are measuring, and we know the temperature. So how, if we substitute these values in these equations, that is the derivations for isothermal and gradient layer, we can obtain the properties at the particular height. So here we are seeing the height in both units, feet and meter. So if we are knowing the height h, so we know the base height. When we apply these values, that is the height, altitude, and temperature, we obtain the pressure. And similar pattern, we can also obtain the density. And similarly, when we plot this, that is the pressure, temperature, and further whatever the calculation is, that is the density or speed of sound with altitude, that is these terms, the pressure, temperature, and whatever we are measuring are taken in x-axis, and the altitude is taken in y-axis. So this is a basic common reference factor. So with altitude, we can see the variation of pressure, density, temperature. So here we can see that at particular height, that is approximately consider this to be 1000 meters or 300 meters. So if we plot this value over here, and for this perspective value, if we plot the value of the pressure temperature at a particular position in x-axis, we will be obtaining the standard atmosphere model. This is also known as International Standard Atmosphere Model. Here we can see that this varies along different layers of atmosphere, starting from troposphere to stratosphere to mesosphere to thermosphere and furthermore. And this image also helps us know what are the activities or common presence in that layer of atmosphere. So in order to get a detailed perspective of this concept, that is atmosphere, its properties and standard atmosphere, you can typically refer these pages or chapters in the book Introduction to Flight, 7th edition by John D. Anderson. The page number is mentioned over here, and this is specific to the 7th edition. And Aircraft Performance and Design by John D. Anderson, and the page numbers are 545 to 565. And these may be available with your college library or some other resources. We did learn about the properties of atmosphere, and we have derived and seen the international standard atmosphere chart of the standard atmosphere model. That's it for this session. Thank you. Let's crack Gate Aerospace.